Hello, my name is Jenny Thorvaldsen. I'm the Chief Economist and Director of Data Development at IMPLAN, and today I'm going to talk about the RAS technique for balancing matrices. And this is really fundamental, this RAS technique, to creating the annual databases that IMPLAN puts forth, as well as the entire input-output modeling system, because it's based on a matrix, which is the social accounting matrix, and that matrix needs to be balanced. And so the RAS technique is usually used for that. So we'll just talk about that a little bit today. So without further ado, I'm going to share my screen and start a presentation. And we'll talk a little bit about what the RAS technique is, how it is used, particularly as it pertains to IMPLAN, and then we'll, a couple important things to realize or note about the RAS technique, and then we'll do an example in Excel. Okay, so before we get started, just want to mention that RAS is not an acronym. It really just, those letters refer to the variables when the RAS technique is written out in equation form. So what is RAS? It's a widely used methodology to balance matrices, as I mentioned. And what do we mean by balanced in this context? We mean that all the values in each row of the matrix sum up to each of those rows' control totals. And the sum of, at the same time, simultaneously, the sum of all the values going down the columns in the matrix equal each of those columns' control totals. And by control total, basically what I mean is usually we know what those values, the column totals and the row totals should be. We have good data on those. That is typically the case, or even if we don't, it's an estimate that we feel good about, and then all the values inside the matrix can adjust accordingly so that they sum to these control totals. So why would a matrix be unbalanced? One case would be when some values in the matrix are missing and they must be estimated. So that happens to us all the time here at IMPLAN when we're estimating data that we want to balance across industry hierarchies and across geographical hierarchies at the same time. And there are a lot of missing numbers that IMPLAN estimates. And it would be quite the feat if all of our first estimates resulted in a balanced matrix. Because as you can imagine, so a matrix has rows and columns, and there's some values within that matrix that are missing, and we'll put an estimate in there, and that estimate then must adhere to its row control total as well as its column control total, because each value in a matrix belongs to a row and a column. So obeying both of those at the same time with our first estimate would be quite the feat. So usually we have a lot of estimates that we put in there, and that makes it such that the sum of the values in a row don't equal that good control value we have that the sum of the values in that row need to equal. And therefore we have to adjust up or down the values in that row so that they do sum to that, okay? And we'll get into more of that later. Another reason, a case for the RAS would be when new row and column totals become available and we want to update all the values inside the matrix to sum to those new control totals. So some practical uses: updating input-output SAMs. So as I mentioned, social accounting matrices are kind of the backbone of input-output models like IMPLAN. And such models are based on the BEA benchmark IO tables, but those are released just every 5 years. And so we use that base benchmark matrix for 5 years before we get a new one, but we update a bunch of values within that matrix and the control values on the outside of that matrix. And so we update a bunch of numbers in there, and then we have to rebalance everything to make sure that they balance. Vasily Leontief, known as the kind of the father of input-output modeling, was the first to use the RAS technique in this setting, but credit needs to be given to Richard Stone, who really waved the banner for this and championed this the use of this technique within the field. And then also creating SAMs for sub-national regions. So those BEA benchmark IO tables that are released every 5 years, they are just for the country as a whole. And so we at IMPLAN, we create SAMs for every state in the nation, every county in the nation, every zip code in the nation, as well as statistical metropolitan areas and congressional districts. And so once you regionalize a SAM, you have to balance it again. Okay, and then also ensuring the economic data estimates balance across geographical and industrial hierarchies at the same time. And I mentioned that to you previously. And that's the example we'll do at the end. All right, so how does a RAS work? It is known as biproportional balancing, and it's an iterative process. So the first step would be to balance the rows by adjusting the values in each row by the ratio of that row's control total to the current sum of all the values in that row. So for an example, let's say that the sum of values in a row is 90, but the control total is 100. Well, that means our estimates are too small and we need to bump them up so that they sum up to 100. So how do we know how much to bump them up? Well, as written here, we take the control total divided by their current sum. So in this case, it would be 100 divided by 90, which is 1.11. The new values, once we do this, will sum to 100. But once we do this, the columns are out of balance. So now we need to balance the columns by doing the same thing, but to the columns. So we adjust all the values in each column by the ratio of the column's control total to the current sum of values in that column. So it's doing the same thing, but we're going vertically instead of horizontally. But as soon as we do this, when you adjust values in a column, like I mentioned before, each of those values also belongs to a row, and the rows were balanced, and now you've changed values in the column, which means they know then that value, the row that it belongs in will no longer be balanced. So we have to go back and rebalance the rows. But the important thing to note is that now when we go back to rebalance the rows aren't as unbalanced as before. Each time we do this, the amount of unbalance gets smaller and smaller each time. So step 3 will be to rebalance the rows. But in our example, let's say that now the sum of the values in our row is 98 instead of 90. So we're more balanced than we were the first time. And now each value in that row, still too small, but less so. And this time they'll be multiplied by 100 divided by 98 instead of 100 divided by 90. So now we're multiplying them by 1.02 instead of 1.11. And once we do that, again, they're balanced, they sum to 100, but now our columns are a little bit unbalanced again, but less so. So we rebalance them and we go back and forth until all the rows and columns are balanced. Okay, a couple challenges I want to point out before going into our example. One is holding known values fixed, okay? So it's usually the case that you're not adjusting all the values in a matrix. Some values might be raw data that is a known value that is good, and you don't want to change that value. You just want to change the ones that are estimates. Like I had mentioned before, a lot of times you're going to have missing values that you throw in an estimate for. Those are the ones you want to adjust. So you want to adjust your estimates so that they are in accordance with some known values in the matrix, as well as that known control total as well. So let me give you a simple example. So let's say here are and I'm just going to do it for a row, not for a whole matrix. So this is just part of a matrix. We're going to look at a row balance. And here are our, let's suppose that we have these 5 values here, 15, 50, 35, 40, and 20. They sum to 160, but our control total is 100. Now let's suppose that 50 is a known value and the rest are estimates. Well, if we just divide our control value by our current sum, then our adjustment factor is 0.625. And if we multiply all of these values by 0.625, we're sure enough going to get a row that sums to 100. That seems great, but look what happened. We changed a known value, and now we have a value that's 31.25. And someone's going to call you out on that and say, no, 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 I saw it published in some public data source that that value is 50. You guys messed this up. So what we want to do is hold that value known and just adjust the rest of them. Okay, so how we do that is now we don't want to adjust all the numbers so that they sum to 100. What we want to do is adjust all the numbers, the unknown numbers, to the control total less the known values. Okay, so how we do this is first sum up just the non-disclosed values. That's that ND here, basically unknown values, values that are estimates of ours. So they were non-disclosed and we provided estimates for them. And the sum of those numbers is 110. And the control value less the known value. So remember, our control total for this row was 100. But we're going to subtract off 50 because 50 was a known number. So we're left over with 50 left over, a value of 50 that's left over that can be assigned or distributed to all these unknown values. So we get a ratio of the control value after we've subtracted off the known values, and we divide that by the sum of the estimates of the unknown values. So 50 divided by 110 gives us 0.4545, a different adjustment factor. And that adjustment factor gets multiplied only by our first estimates. So we're just leaving that 50 value alone because it's known and it's good. And so we calculate an adjustment factor that's just related to our estimates and how much total value we can give to all those estimates. So we multiply 15, 35, 40, and 20, all those numbers by 0.4545, and look what we get. So those numbers get adjusted more down farther because we're leaving 50 alone. And then the sum of all those values becomes 100, again, without having touched that known value. So that's something to keep in mind. Another thing to keep in mind is negative values. Now, the technique I've described thus far back here, this only works if it's all positive values in your matrix. Okay, it won't work if you've got a mix of positive and negative values. So let's suppose you have a matrix with a mix of negatives and positives in it. And if the current sum of values is too small, all the values are going to be multiplied by some value that's greater than 1, right, to bump them up. But that means that the negative values will become even larger, meaning more negative. And if we're trying to bump up the sum of the values in a row, having something become more negative makes it harder to do that because that's pulling that sum farther down, which means that the positive values have to overcompensate for that. So the positive values in that row become really, really big to compensate for the negative values that are becoming bigger. And so values just start blowing up and getting way too big. So the RAS will work, but you're not going to get good estimates. You're going to get very extreme values, positives that are too big and negatives that are too big. In other words, all values are too large because the positive values have to become even more positive to outweigh the negative values that have become more negative because you're multiplying everything by a value that's greater than 1. So everything's becoming bigger. And the same thing would happen in the alternate case. Basically, analogous thing would happen. If the current sum of values is too large, then all values need to shrink. So they're going to be multiplied by a value of a value that's less than 1, which means that negative values will become smaller, that is, less negative. Okay, but then we need our positives become, what we ideally would want is that the positive numbers become smaller and negative values actually become larger. We want them to become more negative, right? And that doesn't happen with a straight RAS. So let me just give you another simple example. So here in this example, we just have one negative value. It's negative 40. Now, if we just did a straight RAS on this row, then you see that our sum is 120 and our control value is 100. That gives us an adjustment factor of 0.833333, okay? If we apply that, then we have these balanced values that do sum to 100, but our negative value became smaller, and therefore our positive numbers so that negative number became less negative. So our positive numbers have to become even smaller than they really should. And so there are techniques to use RAS in a way that kind of balances negatives differently than positives. So you don't get this out of control extreme numbers where positives have to become super positive to compensate for negatives that are becoming more negative, and vice versa. And we at IMPLAN have a special proprietary technique to accomplish a RAS with negative values in a way that doesn't blow values up. But it is proprietary, so I won't go into it in this video. Okay, finally, we'll end with a practical example. One of the data sources that IMPLAN uses is the BEA's Regional Economic Accounts data, and it gives us employment and income by industry. But it has an industry hierarchy. So in this example, these are real industries in that data set, and they have a parent. So we have a parent industry, which is called finance and insurance, and it has 5 child industries, we call them, or child sectors. And when we estimate numbers for these child sectors, we need those to sum up to their known. We're going to assume that the parent industry has a known value, and so we need to make sure that our estimates for the children's sectors sum up to that known parent sector value. But at the same time, for each of those children's sectors, we also have to make sure that our estimates for all the counties in a state for each of those given sectors sums up to some known state value for that sector, okay? So that's where it's kind of like a matrix. It's something that has to be balanced in 2 directions. Okay, so let's pull open Excel, and I'm going to walk through this example just briefly, just to show you what it looks like. So I've got some fake numbers here for our 5 child sectors and our parent sector. Okay, so I've got the sectors going this way, and then I've got geography going down here. So the counties have to sum to some known state value, and the sectors have to sum to some known parent sector value, okay? Oh, one thing I didn't point out in yet, and I have it asterisked here, is that the RAS procedure will never change a 0 to a non-zero or vice versa. It only adjusts non-zero values either up or down. Okay, and we're assuming the row and column controls are always fixed, and so they're unchangeable within a RAS, and that means they either are known public, raw data that you don't want to change, or they've been vetted prior to entering the RAS and you think that's a good control value. Okay, now here's our matrix that we want to balance, and I've got some highlighted in yellow, and we're going to assume that those are known values that we don't want to change. Okay, well, you can see right off the bat that this matrix is unbalanced because You can see here, I've got sums. I'm summing all the rows, and they don't equal their control values. And here are the discrepancies. So this is basically just our sum minus what it should be. So some of the column or some of the rows are, their estimates are too high and some are too low. And same with our columns right here. We can see that our column sums don't equal the control totals. The control totals are the things in gray. So here I've summed them. Comparing that to the gray number 500 means our numbers are too big, and the discrepancy, we need to make our numbers smaller, our estimates smaller by 50, okay? So this is just our unbalanced sum. Now remember, let's, we go back and forth iteratively. This one, in this case, it doesn't really matter if you start with a column or a row. In this case, we're gonna balance the column first, okay? So how do we do that? Well, first calculate the sum of non-disclosed values. Remember, we're not messing with the known values. So I just took the known values out for right now, okay? We're not gonna worry about them. We're gonna put them back in later. Let's just focus on these non-disclosed values, our estimates of them. And they sum up to, for this row, 195. And the leftover that they're supposed to sum up to is 145. How did I get that? Well, I got that by taking the original column control total of 500 and subtracting off the known values. Okay, that means that what's left over, 500 minus those known values, is 145. That means the sum of these guys, the unknown values that we're providing estimates for, they have to sum up to 145, okay? And so same thing for all the columns here. Okay, then I calculate these, I put these into ratios. Calculate each non-disclosed value's proportion of their sum, okay? So each of these is saying how much of the sum of current estimates is this guy. So 20 divided by 195, okay? And this one's gonna be 80 divided by 195. This one's gonna be 90. So we're just getting proportions of these guys, okay? Then we multiply each of these guys' proportions by that leftover value that they need to sum up to. Okay, so these proportions should sum to 1. Let's check. Sum, do this on the fly. Let's hope this sums to 1. All right, let me give it some decimals to make sure. Okay, sure enough, they sum to 1. So all we're doing is we're using these proportions to proportion out this 145, because we know they have to equal, these estimates have to sum up to 145. So now we take 145 and multiply it by each of these proportions, okay? And so that proportions out 145 among these estimated values. And so then we're left with the sum. Let's check our sum. Yep, that's the sum of our estimates. Now they sum to 145. Now if I put the disclosed values back in, pop those guys back in, and get a total column sum, lo and behold, they sum to 500. Beautiful. So my columns are balanced. They match. The sum of all the values in each column matches that column's control total. So that is just showing you how to balance a column. You would do the same thing analogously going across the rows. And then once you did that, so I'm not going to step through that because it's just going to take too long, but we do a row balance, and we're going to do the same thing, summing up the non-disclosed values, calculating proportions, multiplying them by the leftover that can go to non-disclosed values, putting the disclosed values back in, and we've got balanced rows. What I wanted to show you here, just to show you, to notice that once we balance those rows, our columns are unbalanced again. But notice that the column discrepancies are smaller than they were before. Let's just look at this first one. The discrepancy, they're off just by 27. Whereas when we started this thing, they were off by 50. Okay, so the discrepancies are getting smaller and smaller each time we do this. Okay, and that's really all I had for today. Thank you for watching and hope to see you again.